So, guys, thank you very much for being here today. Yeah, this is my first Friday talk. As you may know, I'm not like a technical person, so I will try my best to talk to you. But the idea of the presentation is not to be like technical, is that we cover different aspects, business, technical, and also the basics of of the technique. So yeah, let's move to here. So who am I? To those who doesn't know me, I was born and raised in Brazil, and I'm living in Lisbon right now. I call myself a product person. I'm graduated in IT and journalism. And other than that, I'm finishing my MBA in data science and analytics. I just added this here because this is the origin of this presentation. So this is the agenda. As you can see, it's quite packed. We will gonna through all these topics, and I don't want to spend time here. So let's talk about heart failure and forecasting heart failure using the decision tree. Before that, I will give you some basics, and then in the end, probably in the second half of this hour, we will go to code and check the everything. So starting point, what is heart failure? So heart failure, which causes the heart attack, is part of the group of cardiovascular disease in which the heart is unable to pump blood in a manner that meets all the metabolic needs of tissues with an adequate amount of blood. Shortly is when the heart is weak and is unable to make the blood circulate throughout the whole body in a good manner. So this is heart failure. Heart attack in numbers or heart failure in numbers, let's say. So this is 18 million people die every year from cardiovascular disease. So as you can see, this is a huge problem for the humanity, let's say. And more than 14 million people die due to heart attacks and strokes. I started figuring out how can I represent 14 million people to this group, and I got this number. Oh, Jesus, this one. So it's pretty much the population of Serbia, Bosnia, and Croatia together, 14 million people. So as you can see, it's something that kills a lot during every single year. So briefly, let's talk about artificial intelligence. I think this is the base ground for everybody. So what is it? Is technology that enables computers to simulate human intelligence and problem-solving capabilities. Why did I bring this slide here? Because every time nowadays that we think about AI, we think about LLMs. And yes, for sure, LLM is AI. But what about clustering when you get data and the computer is able to split them in different groups? This is also AI because it's enable computers to simulate human intelligence. And what about linear regression when you predict something based on the data that you have? Of course, there are way more examples of this, but this is just to, I don't know how many of you thinks that AI is only LLM. It's not. So AI is around for more than 30, 50 years right now. So yeah, let's dive a little bit into the types of algorithms. This is quote unquote because depending on how you organize it, you can have more or less types of algorithms. But let's talk about at least some types of algorithms. So first of all, you have the regression algorithm. This is used to forecast discrete value or integer in the end, making it more understandable, I would say. It's like how many people will be alive by 2037. So it will be an integer in the end. So it's a regression of a discrete value, or how many cevapi, sorry for the pronunciation, will be sold next year in Serbia and Bosnia. It will never be 12.5 cevapis, right? So it's a discrete value or an integer in the end. And for the regression algorithms, you also have the algorithms that will forecast continuous value, which means decimal. How much an Apple share will cost by 31st of December 2026? This will be for sure some number with decimal. I don't know how much it costs today, but it will be something with decimal points. And there is this one. How much will my company sell in 2027? Of course, the answer will be in with decimal points. And here we can argue, okay, but I don't need to be that specific that needs the decimal point. So I can use for the same question, I can answer that using the algorithms forecasting discrete values. Of course you can, and it won't make any difference in the answer. But anyway, I want to bring these two regression types for you. And so you get more comfortable with that. And there is another type of algorithms with it, the classification algorithms. What does it does? It normally, and it also has two categories. So it classifies the target variable, or what you were trying to forecast, the first type in two categories, which means, Anya, now is the time. Is it a dog? True or false? So you want to forecast something that it's classified in just two categories, dog or not dog. By the way, this is my dog. I just want to to put him here. And then we have it's pretty much the same thing, but it's a bit different. It's the same thing. We have the multinomial when you need to classify something in three or more categories. And for this question, what is it? Is it a dog, a capybara, a donkey, or a cat? I don't.
Capybara.
Yeah, you're right. So this is a capybara. So for this case, we also use classification algorithms, but multinomial and not binomial. Yeah, let's think about the problem that I proposed for this talk. So giving the patient data information, classify whether the patient death event, I use that because this is what is in the database, is true or false, right? So which algorithm types should be used for that case specific? So we know that the regression algorithms are for discrete or continuous value. And then we know that the classification algorithms are used for classifying. So hopefully you got that we would use the binomial classification or binary classification because we need to answer to this question. Is it a death event, true or false? So let's have just a quick glimpse in the database so we understand a little bit something and some important aspects of the case study here. So this is the summary of the database that I will be sharing with you. The project is also in a GitHub repository, so we will have access to that. So first thing, every time that you are trying to analyze something to create a model, is very important that you check the summary of your database. It's crucial that you understand if your data types are the right data types. So let's see here, like anemia. Anemia is true or false. It needs to be as Boolean in the database or the related one factor in R, because otherwise the algorithm will see that as a number. Imagine that it is an integer and not like a category, and that will like make the algorithm go simply wrong. Another very important thing is to check, like, as you can see, the first variable is age. For this database, we have observations, which are the patients, that goes from 40 years to 95 years. It's important to you to know that if you want to forecast someone who has 35 years, who is 35 years old, you cannot use the model that we will create here. So the model that we are going to create will be useful for forecasting people from 40 until 95 years. And that goes for all the boundaries that we have in all the columns or variables. So this is very important. Another thing, it's a jargon. Jovica told me to avoid jargons, but I'm bringing that to you because I need to use them in the future. So normally in the data science and data analytics, there are several names for those, but some literature classify the columns or the variables as features. So you have features, and the main goal of the feature is to explain the target variable. Okay, so the main idea of everything is I group a bunch of information that will calculate something and will be able to classify, in your case, if the death event is false or true, 0 or 1. This is very important. Features and target is very important. And in our target variable here, as we can see, we have more observations which are not death events, so people didn't die, than observations where people die. And this is quite common, especially in health studies, because, yeah, normally people don't die. And we do several exams until we get there, right? We need to go day by day. But this difference here may result in a classifier that is biased towards the majority class. To sum up, that is the algorithm will know more about not death cases than death cases. So these are the things that I want to highlight here in the database with you. Let's move next. Algorithms. For this binomial classification, I brought some algorithms that are capable of classifying this, or that we can create models to classify death events, yes or no. So the decision tree is one of them. Naive Bayes is another model, another technique. Gradient boosting, support vector machines, logistic regression, and more. Obviously, today we will be talking about the decision tree, but in my master's, I created all these models and compared them all to, yeah, in my work, but it doesn't matter. So what is decision tree? Decision tree is a machine learning algorithms utilizes for classification and regression tasks. So it's very nice because you can either classify whether it is a capybara or not, or you can classify whether it is a dog, a capybara, a cat, or I don't remember the last animal that I put there. So it has a hierarchical tree structure, which consists of a root node, branches, internal nodes, and leaf nodes. I don't think the structure aquí is unfamiliar to anyone. So let's move to the okay. So let's see the pros for this algorithm. It's a powerful and easy to understand technique. As you can see here, and as we're gonna see in the future with real data, it's easy to understand. easy to implement and fast to execute. We will see that and we will execute several times. The model is easy to understand. The first one is the technique is easy to understand. And this one is the model itself is easy to understand when working with few variables or features. Yeah, I use features here. So if you have like 1,000 features or variables, imagine how big would this tree be. But for like 12, like 13, something like that, we will be working today is perfectly fine. The cons of it is hard to understand when working with many features. I just explained that. And when you are working with many features, the performance can be affected because the tree is very large. And the structure can become hard to understand since you cannot visualize that in the way that we are going to visualize today. And it will bring you different situations that you need to do other things to be able to see the tree. And last but not least, it tends to overfitting. We're gonna see something about this overfitting technique or problem. And yeah, hopefully at the end you understand what overfitting means and how to avoid it. So right now, a step forward is check the main items for the classification algorithm. So we have the cutoff. I will explain that in details. Confusion matrix. The confusion matrix is based on the cutoff that generate metrics, and the metrics that we are going to see today is the accuracy, the sensitivity, specificity, and precision. So let's see what cutoff means. So cutoff allows you to determine the cut point for classifying classes. Predicted values that exceed the classification cutoff are classified as positive, otherwise as negative. Blah, blah, blah. Behind us, let's use this quite common Java function to explain that, and then I will explain in the algorithm answer as well. So when you enter a 74.65 to a math round function, you get 75 on the other side, right? This is pretty much because the math round is using the cutoff 0.5 in the decimal point, right? Imagine that the input was 74.49. It's less than 0.50, so the output would be 74. It's exact, the cutoff is this. So when you forecast something with the model that you have created, you will receive something like that back. So you will receive for your observation X, the probability of being 0 is 14% for the first row and 85% in the second row. And that goes on for all the observations. So this is the answer from the algorithm. Let's see now how the cutoff can modify the real answer for your algorithm. So let's think if we have a cutoff of 0.5, which is the normal one, the most common one, what would be the output, the real output for the algorithm? So is it 0.5 greater than 0.85, sorry, greater than 0.5? Yes, it is. So it's 1, it's death event. The second one is 0.03 greater than 0.5? No, it's not, so it's not that. Is 0.57 greater? Yeah, so it's 1. Is 0.49 greater than 0.5? No, so it's 0. It's death, not death, death, not death. What about if we use the cutoff of 0.6? So I won't go, but only the first observation is greater than the result is greater than 0.6, so it would be the only one that would receive death event equals true. Just for extrapolation purpose, let's see the last one. If the cutoff is 0.86, how would the response looks like? And this is very important because of the next. Is it okay? Is it so difficult? Any questions? Okay. So let's talk about confusion matrix. Now that we have an algorithm which is giving us some answer, and we define the cutoff so we are able to classify 1 or 0. The confusion matrix is a table that compares the real value with the predicted value. So this is how the confusion matrix look like. So in lines, you have the actual classes, what is in the database. In the columns, you have the predicted classes. And here you have when it's a negative and negative, you predicted negative, and in the database is negative, you have a true negatives. When it is one, you have the true positive, false positive, and false negative. Let's explore that to make it easy to understand. So let's imagine this case. So the first observation in the database is set as not death, and your model predicted as not death. What is this? This is a true negative, right? So in that case, the confusion matrix will receive 1. Another example would be, okay, the second one, the real data is death, and the predicted value is also death. And then this is a true positive. The confusion matrix will receive 1 in this database. Of course, we have a second row with the same information from 1 would add to 2 and so on, right? And then this third scenario, which is not death in the database, in the real data, and we predicted as 1. What you have here, we have a false positive. So our model predicted as positive, but it's not positive. And last but not least, for sure, if the database says it's a death and the predicted value is not a death, this is a false negative. So the confusion matrix for this table would look like that, 1 in every single cell. Now let's check the metrics that are based. No, let's just go back. Imagine that we change the cutoff when creating this database, the predicted would be different, could be different because of the percentages. And then this confusion matrix also would change just because you are using another cutoff. And now, based on the confusion matrix, we have some metrics, sorry. So let's get this confusion matrix as reality, so that the cutoff 0.6 was used to create that. And now we need to understand the metrics some metrics, there are more metrics. I don't want to keep here talking for 3 hours, but I brought the main ones for our purpose today. So you have the accuracy. Accuracy, I call like the bullseye's rate. Is the proportion of positive and negatives that your model was able to reply to. So in this case here is 150 plus 60 divided by the sum of everything. For this case would be 85%. So which means my model was capable of getting right 84% of all cases that exists on the database. The second one is sensitivity. for this one is, imagine that we have a couple of positives in the database, and I want to know from those positives, those positives that we have in the database, what's the proportion my model has captured right? So this is called the sensitivity. How much the proportion of right predictions checking from the database to my model. The third one, specificity, is the same thing that sensitivity. I know this is quite weird. I took like several hours to understand that. The specificity is the same thing that the sensitivity, but looking to the negatives. So it compares the proportion of negatives in the database and your proportion of right negatives that the model was able to capture. And the last one is precision. And precision is the positive as well, but from your model to the database. So from all positive results that you got from your model, what's the proportion of those that were also positive in the database? Yeah, I know it's not I think so easy to understand, but let's move forward. So right now here I bring to you some results from the database that we'll be working with the different cutoffs, the confusion matrix, and the metrics that it generates for you, right? So, but more than the metrics here, I want to discuss with you something which is, let's get this this one in the middle and try to understand that. So the true negatives and true positives are okay. So my model was able to capture it right? But what about the false positives? This means my model says that 5 people were positive or need to get a treatment anyway. Yeah. So 5 people need to get treatment for heart failure, but they were not ill for this case. So it's a kind of a problem, right? Because we are sending people to get meds that they don't need. And on the other hand, if you get the false negative, 28 people that should receive treatment is not being flagged as like death event for our algorithm. So why I'm bringing this up, because more than just the numbers, the proportion, it's in that case that we are talking about health. It's important to understand that 5 people can be some of us and one of the 28 can be some of our parents, I don't know. So it's very important, more than the numbers, more than the techniques, the confusion matrix, that you feel the number so you can make some changes on the model when training the model, when checking it, to be able to get the best model that you can, so you can save more people in the end. Yeah, last concept, guys, and then we are moving to the code, right? The train test split. Maybe some of you have seen that before. So what's the idea behind that? You have your data set, your observation, the whole thing, and you split that into train and test. Normally it's somewhere from 70% to 90% for training and the difference for testing. And then you get your train database, you train your model with that. We're gonna do that. And then you get the metrics from the forecasts. After that, you get the tests. you run your model that was created with the train data set, you run the predictions, and you get the metrics. But okay, but why do I need to have this split, right? Because when you train the data set, when you train the model, you are saying to the model, look at this data and create something behind that so you can forecast that event. If you train the model with the whole data, when you're going to test it, the model already has seen that data. So if you split that, you train the model with a data and you test the model with an unknown data, you will get something probably like that. The metrics in the test part will be lower than the metrics in the train part. Why? Because the model have never seen the data that is in the test partition of the data set. And what's the goal here? The goal is trying to find the best tune in your model to have these both metrics on train and tests as balanced as possible. So this is the main thing. So you train your model, you run, you get the metrics, and you check against the metrics generated with the tests. If they are too far, trying to find another way that those metrics, in general, the metrics in the tests database will be lower, always lower, but it should be close to the train one. So just to you to know where we are in the agenda, we have pretty much everything done so far. So let's move to the code. I will make the code available to you, and since it's in R and you probably have never worked with R, I add this blog post as well that can help you installing R. So this is the R environment. I will try to make it bigger for you. I will clean here. Yes. So this is the project that we'll be downloading is this one. So we have three main scripts here and the project file and the data set that we'll be working. It's inside of this folder here. So in your machine, just run the first script. It will load all the packages and install all the packages that you need. And then the second one is to load the data set. And here I did some transformations to make the data types the right ones and a bunch of small things and some you can see here like the 5 first columns of the data set. But let's go to the decision tree. So first of all, you need to set the seed. This is needed every time. Probably all of you knows why this is needed. If not, we can talk about that later, but I cannot take time right now to explain that. And the first thing, so our database is here. Let me show you. It's this DF. So here is our database, all the features, the target variable, all observations, and everything. The first thing that we are going to do is to split in train and test, 80% for training and 20% for testing. So it's just, you just need to execute from line 7 to line 13, and you have the train data set, which is 239, which has 239 lines, and the test data set, which has 60 observation on that. Now that we have the train and test, we can train the model. So I'm using this package, the R part, to create the model. And let's see what is needed to train the model, right? So I will save the model in this variable, tree model. The first thing, I send the data to it, which I will send the train data. I will set which method I want for the algorithm to be trained with. So remember that the decision tree is able to classify or to make classification tasks and regression tasks. So we need to inform the class. And this one is this parameter here is to receive that something is to receive, where is it? Jesus. No, 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 no. So it's this one. Without that parameter, you won't receive this table as response. You would receive just a 0 or a 1 with cutoff of 0.5. I wrote it here. And now let's go to the formula, right? The formula is the important thing here. So the formula starts with what is your target variable? So just to remember, the target variable in our case is the death event. And then you say, okay, I want that to be calculated based on these variables. And the point, the dot here is like the asterisk, is everything. So I'm getting all the features and to determine which death, whether it is a death event or not. There are other ways to make this formula. So you can do like this. You can say death event in relation to age plus anemia plus another feature plus. Or you can use another thing, which is like death event in relation to everything, but or remove time and diabetes from the list of features that you will train the model. So right now I use this one, which is that event in relation to all features. And here we have some fine-tuning capabilities of the model. We will play around with that. But the mean split, remember that it's a tree. And the mean split means how many observations is the minimum for each tree to have. So imagine that it's 15, like this. If a node has 16 observation, it will try to split. Otherwise, less than 15, it will say, okay, this is the end of this part of the tree. Max death is how death the tree should be. We're gonna change that, and you will see in practice. And this CP is a complexity parameter. It's very mathematical. I don't want to bother you more with that. But the important thing is know that small numbers encourage large trees and large numbers encourage small trees. So we're going to see that in practice in a bit. So I will create the model here. So remember, formula is that event in relation to everything. And then let's see how the model looks like. So this is the model that was created using the training data. So you have the root node and then all the nodes until the end here. The percentage here, it's how much the proportion of the data set that falls in that node. So as you can see here, 74 and 26. If you sum those up, you have 100, right? And then if you sum, so this is in general. So from this 74, 45% of the database goes to this branch here in this tree that we just have created. And the middle, this is the class, so it's for class 0, and in the middle you have the probability of this to happen. In other words, you can say that if the probability of 0 to happen is 15%, the probability of 1 to happen is 85%. So now I will predict using the model that we just created. So I will use this predict function, and I will pass to this the tree that we have created here, and also the data set that I want it to predict for me. So let's run that, and let's check the 10 first items of the probability. So for the training database, we have this one. The first observation is 100% sure, this algorithm says, that is 100% sure to be death. The fourth is 76% of being deaf and 23% of not being deaf. Now that we know, we need to apply the cutoff on that, and we will be able to create the confusion matrix about that. So I will apply the cutoff of 0.5 first. I will truly apply that, and then this table function creates the confusion matrix to us. So let's execute that and see it's down here, the confusion matrix. So for this algorithm, with this cutoff, the confusion matrix looks like that. 149 for true negatives, 66 for true positives, 9 false positives, and 15 false negatives. Right, so let's just see the metrics. Don't bother with that, guys, because it will be an easy way to check that. But this is the accuracy, 89%, sensitivity, 81%, specificity, 94%, and precision, 88%. Now, let's forecast using the test data. Remember that we create the model with the training data. Let's do the same thing, but predicting the test data and check and see the confusion matrix for the test data. So those are the 10 first answers. I will create using the same cutoff, 0.5%. So this is how the confusion matrix in the test data looks like. I will go down, and this is the accuracy, 81%, 66 for sensitivity, specificity 86, and 0.62 for precision. Let me execute the whole thing, and then we will be able to see here in just one thing. So in this table shows the first two lines is the confusion matrix for the training data, and the third and fourth line is the confusion matrix for the test data. So let's remember that this one, if we're gonna check the people that are in the test data, 6 people would be sent to treatment without the need, and 5 people out of this amount will be not sent to treatment, even though it was needed. Let's check the metrics. So here we have the metric. So accuracy on training data is 89% and test data 81. Sensitivity 81 in the training, 66 in the test. Specificity 94. against 86, and then precision 88 against 62. As you can see here, that thing that normally happens happened. So the forecasts in the training data are better than in the test data, right? Why? Because the algorithm was trained using the train data. So it's a data that the algorithm already knew. This is the tree. So let's make some changes here and see how it goes, how the tree moves, and also how this matrix changes according to this. So I will first of all, I will change the min split. So the minimum amount of observation in each node, I will move to 10, and the max depth I will put to 20, and the CP to 0.1. I will execute everything just to see the metrics. It will execute the whole script. So right now, let's check, first of all, our tree. So if you check the tree, it's shitty, right? Because the tree, the whole thing, it's being classified using only time as something useful. But if you check the numbers are quite okay. There is no that much difference between the metrics and between train and test for all of them. And here, one thing, so even though the max depth is 20, we just got one level down. Let's change just the CP, the complexity, for 0.1 and see how the tree will look like. So now the tree looks like that. It's more deep, for sure. Instead of just one level, it has 1, 2, 3, 4, 5 levels. It looks better than the previous one, but let's check also the numbers. The numbers are still far away from each other, right? So 92% in accuracy in training and 81.67 in tests. It's, even though it's okay, it's a good number, 81%, it's not that bad, but it's far away from each other. Let's now change the minimum split to 1. So we started with 20 or 15, and then we changed to 10, the minimum amount in the cell. And now let's go back to just 1. Execute everything. Let's see the tree right now. So the tree is way more complex. As you can see right now, it's pretty much impossible to see, and we only have 11, 12 target variables, but it's just pretty much, let me just execute again, pretty much impossible to understand the tree in a visual manner. But right now we have 1, 2, 3, 4, 5, 6, 7 levels deep. Now, just to you to see, if we change that to 5, even though the max split is just 1, where is it? Here. Now we only have 5 levels down in the decision tree. Yeah, and this is pretty much it, guys. So of course we can, the main thing right now is to start playing with everything, with this fine-tuning parameters, so you'll be able to find the best decision tree model for this data. There is no real answer. The one for in my capstone project, The one that I considered to be the best answer was this one, exactly this fine-tuning model with all in this formula, all these parameters with this formula. That was the best one that I found that did not overfit the data. Yeah, that's it. In the end, there is no final answer to you. You can use that. You forecast 82% right, which is a good number. However, I can tell you that the other models that I had worked with brought a better accuracy and just one thing more, but brought a better accuracy and sensitivity and specificity than this one. I just want you to check one thing. So I don't know if you have checked that or seen that, but every time the sensitivity and the precision metrics were below the accuracy and the specificity. Those metrics related to the true positive items of your forecast. In the end, remember that the database is unbalanced towards the negative observation. So this probably explains why you always have better negative, everything that connects to the negative forecasts are higher than the positive forecasts. Yeah, I think, sorry guys, I know it's too much. I compressed 8 hours in just 1 hour, but hopefully you got something. And now I want to know, what questions do you have?
I have one question. First of all, thanks for the presentation. I really liked how you showed how the model reacts as you change the hyperparameters. But I was always curious, is it possible to implicitly overfit to the test data by changing the parameters of the model as you see the performance of the model? So for example, you see the performance is not that good on the test data, and then you try to tweak the parameters. And my worry is that this somehow implicitly overfits the model to the test data, even though it doesn't see the test data.
No, it can happen because everything, but it won't be very. This is what you need to do, actually. You need to retrain your model based on your test data, because since the model cannot see your test data when it is trained, if that happened, you got like the perfect balance in between. You could find some hyperparameters that were able to create a mathematical model that fit both data sets, you know. Of course, if there is a new bunch of data, you may need to retrain your model with different hyperparameters. Imagine that right now we receive another 300 observation for those cases. Maybe your model hyperparameterized, I don't know how to say that, will not fit anymore to the test data. And then you need to create it again. But it's unlikely for you to be able to overfit your test data from your training data. And yeah, in here, at least just I think if I see, I have overfitted the train right now because everything I could get it right. Let's see how the plot is. It's not that big. I thought it would be bigger. But I have changed some parameters here, right? So I'm accepting one observation in which node. I'm getting the deepest tree possible, and also using a very small, I'm encouraging complexity parameter. I'm encouraging a large tree. Getting that, I got one in the training data, but the test data, you never from there to here. You will always be, or pretty much always, the precision in the training data will be higher.
Thank you.
Jovica, you were about to tell something.
I have another question. Since you said you're a business guy, right? So, yeah, what I want to ask is, do you think that customer can, do you think that you can explain to the customers that they will not get always precise accuracy, and that, for example, that we don't know in advance, are we going to be able to create a model that they will be satisfied with? I mean, in a sense of accuracy, because as you said, for example, if you get another set of data for the same thing, the results can be totally different. For example, they could be like 50% of accuracy. So that's my question to you. So what do you think, especially because of all of the hype, as you said, around AI, and that people that don't understand this, usually that are in business, that make plans and are willing to pay for some creation of this. So how to explain to them? What are your thoughts, and is it possible?
Yeah, so first of all, this is an awesome question because, yeah, it brings a bunch of things to the surface, to the discussion. So first of all, if you get 100% in general for any models, so when we are creating a model, a decision tree, or whatever method, we are using some mathematical structure behind it to create. So if you get 100% accuracy, you are overfitting. Something is wrong with your data types. Something is wrong. And this is overall, and everybody knows that. You know, when after the COVID broke out, and then everybody was confused about the vaccination, whether it makes sense to take the shots or not, but it's only 80%. So it's very important to someone to explain to the business, but I think the business is more used to that, even that, like technical people. It's like when you get a map, you come to Lisbon, you go to the tourist office and you get a map, right, with the main sightseeing points and everything. This is the map. The map is not the reality, it's the representation of the reality. So there won't be any, or not all the things that are in the city are in the map. Even if you think of satellite photos or something like that, because today there is a tree here and tomorrow the tree cannot be here, right? So going back to your question, I think for like marketeers, imagine them, they know that they advertise for 1 million people and that they will never get 100% back. And in this medical area, of course, the difference in between, this is what they say in data analytics, the difference in between, let me just run this again. So the difference between this 81% that we get here and the 19% to get 100%, it's some variables that are not here, are not available to us. You know that today it really matters to you, or you all of the sudden decide to go to get some ice cream. You weren't thinking about that. Something happened. So is this not available feature happen that you decide to do that? So in a bit on the business side, I think people are more used to that, and it's easy to explain because if it is 100%, something is wrong. It's exactly like, how do you know that you go out today and will be back by the end of the day, right?
I mean, in a sense, also to make a deal, for example, because you cannot guarantee anything, right? You can have like 30% of accuracy because the data are not okay, and they have to pay for something, and you cannot promise something because you don't know it. And so maybe some trial period or something like that. So they give you the data, you try different algorithms, and then you make a real deal. I don't know. In that sense, I thought, because
Yeah,
actually you
also,
don't know anything until you see the data and try to do something with the data. That's,
yeah,
yeah, right.
I had these questions here, and uh, I skipped that because we were like, yeah, it was too much thing. But this is one thing. How long would you test your model with real data in real world? And another thing that you mentioned, imagine that I get more data, but can the data collected in Serbia be considered to forecast in Africa or in Brazil or whatever, because we know that there are differences, even though we are the same, there are differences. So this is very crucial, and this is why I brought to make it real, I would use all the algorithm, or at least test most of them, get the one or two that better performed, and check it. And I had another question here that, I remove it, but how long would you use this algorithm that you have tested for, I don't know how long, and check it over to understand, okay, should I keep this one, or another model will be able right now with more information, blah, 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 to perform a better forecast,
Yeah. And are they going to pay for all of those testing? And that at the end, they get like 30% of accuracy. Yeah, that's
Yeah. And
that's tricky.
there are several tests in medicine that are less than 50% has less than 50% accuracy, which is pretty much how it's just flip a coin, right? So it depends on the everything, and your answer also depends on the problem that you were studying, right? Because imagine that you can increase for credit. You can imagine for the bank that is receiving tons of credit requests on a daily basis. If you can add like 3 in this fourth decimal point, for them it's a lot of money for them that they can save, just because. So it's not, of course, the big number. Yeah, the 81% is a big number, but in the credit case, they will every single addition will make them able to pay you in that case, because this is money. They know that they will save way more than they are paying for you. So, for the model, for the problem.
Okay, thanks.
Thank you.
I have a question about the amount of data added for the training. Will it always affect positively adding the new data? Is there some threshold that will just stop making progress in the model efficiency? Do you adjust the other parameters at that point, or?
I don't know. Say again, because I think I got lost in the middle.
For example, I think at least I think that you trained the model with fairly small amount of data.
In this case, was 80%. Yeah, 80%
No,
of
not the exact number of rows, the exact number of inputs, like few hundreds or whatever, right? So what if you have 1,000, and will it then be better? And will it be better with 10,000?
Probably,
it will
probably,
just fall down at some point and hit some threshold and stop improving.
So the more data you have, the more accurate will be. This is for sure. And so I guess there won't be the threshold or the maximum amount that makes sense to train it. I think only happens if the data that you have doesn't vary that much. Imagine that here for this feature, I have 10 parameters. For this one, I have just two, diabetes true or false, ejection fraction another 30. Since it will calculate, okay, this combination of data results to a 1. If you have several times the same row in your, it won't like really be needed for your model to have more data exactly the same. But I think if it is like more dispersed data, so you have like huge amounts of data and huge ranges of data, the more the better. So the more is always the better. I don't know. I don't think there is a threshold in the end.
And if I understood, the goal is to make the accuracy metrics like the close as possible to the test and the train. So that would be example of a good model.
This is an example that the model is balanced. When predicting data that the model knows, the training data, and that they don't know. And the higher the accuracy, the better, because it's the bullseye rate. So you got the positives and the negatives right, But not only this data, since you never have 100%, because it's overfitting, which one of the metrics would you prioritize? So I want to send more people to the doctor, even though they don't need treatment, or I want to send less people to the doctor. And then I will decide, okay, the first one is accuracy for sure, but the second metric that I will prioritize is sensitivity or specificity, depending on the problem. But what you said is right. So accuracy is the important one, and the more balanced is the data in between train and test, the better. For the more generalized are your model, not the better. It's just generalized.
Okay, thank you.
Any other question, guys? If not, thank you very much for being here. Hopefully that was useful. If you want me, I will share with you the links and the presentation. If you want something else, let me know. I'm on Slack and everything. Let's talk about that. See you guys.
Thank you. See you.
Bye.
Thanks.
Thanks.
Bye-bye.
Thank you. Bye.